getting back to physics, are there any questions on what we did last time, or anything that's come up so far? So let's just continue. This is really just a calculation at this point. Well, not quite yet. So it's still a question of setting it up. Then after a while, it just becomes algebra. So I'll remind you what we were doing. We're talking about orbits of both photons, that is, massless particles, and massive particles like planets, treated as point test particles in the field of the sun, gravitational field of the sun, idealized as the Schwarzschild metric, and which is, in the notation I adopted, minus h squared, that is, the line element is this, plus dr squared over h squared plus r squared. The omega squared, this being the usual line element for the sphere in a particular convention of what's theta and what's phi. And h squared, of course, is 1 minus r naught over r. But if you want, this is called the Schwarzschild radius, and it's just the free parameter that characterizes the most general spherically symmetric solution to the Einstein equations with no matter present. And if you want to relate it to the mass of the object that's producing this field, then it's 2gm over c squared if you restore all units. Okay. Then we found there were killing vectors. There were 3 killing vectors, CA, which was the time. Now I'm using, when I write these E's, I'm using the basis vectors of this coordinate system. So in other words, this is the purely time-like basis vector. And by the way, it came up last time, when I say corresponding to the coordinate systems, it means that, for example, the normalization is that of the, how can we say this? So, for example, E T A partial A of T is 1, right? So remember, in a basis vector, in a coordinate chart, the co-basis vectors are just the gradients of the coordinates themselves, and then the dual basis vector, the basis vectors are dual to them. They give a dual basis in the sense that when you take their inner product with the covectors, you get 1 if it's the same coordinate and 0 otherwise. Okay. So in particular, that means that E phi, let's say, A grad A phi, is also, phi is, in the convention I'm using, phi is this coordinate, the whatever it's called, azimuthal coordinate. So this is also 1, so that means that, and that's how this coordinate is normalized. It's actually the rotational killing vector. So it's not normalized to be of unit length, which is what some people are used to in flat space. I mean, just in 3-dimensional spherical coordinates. So it's not the unit normal vector, it's the normal vector belonging to the coordinate system in which phi is one of the coordinates. And then there are these that's the time-like translational killing vector. And then there are 3 rotational killing vectors corresponding to the spherical symmetry that we identified. They're all just related to each other by rotation. This means rotation about the z-axis. This is rotation about the y-axis. And this is rotation about the x-axis. And so this one, if I write it out, what its components are, if I write it out what its value is, then it's EAY minus Y EAX. So it's the coordinate basis, Cartesian coordinate basis vector in the y direction multiplied by x minus the anti-symmetrized thing. Those are the 2 main ones. then we saw that, or in various ways we saw, using symmetry arguments, that if you start off, which is obvious, if you start off rotating in the equatorial plane with respect to this coordinate system, that is, if the planet or photon starts off moving in that plane, it'll never leave that plane. One can see that by symmetry. One can also see that if, in the following way, that if it starts in that plane, then these other two are zero, or I shouldn't say they're zero. The conserved quantities associated with them are zero. So zeta, for example, 2, 3a times PA, which is zeta 2, 3a. Remember, P is always dx d lambda. Or let's say, write it like this if you like. Oops, but they're all A's. So that equals 0, as you can easily convince yourself. For example, if we look at this one, then it's this. If we write out what is this zeta 2, 3, zeta 2, 3, that's what I have to cyclically permute these. What is this supposed to be? Z minus. So if we imagine that we're in the equatorial plane, of course, Z is 0. That's the definition of the equatorial plane. And Y need not be 0, but if it starts moving in the equatorial plane, then the component of its momentum in the Z direction is, of course, 0. And so this will be then, when I dot it into the momentum, I'll get 0. And then conversely, the fact that then it's conserved, of course, and the fact that it's conserved means that this remains 0. And that means that it must stay in the equatorial plane. So anyway, so the upshot is that these two don't give us very much useful information beyond that fact, and the only conservation laws that are really relevant are the ones coming from the time-like killing vector, which we call, of course, energy, and the one coming from the rotational killing vector, which, of course, we call angular momentum. Then we went through and set up what the conserved quantities were. We computed what the conserved quantities were. Oh, and then I should mention there's a third, if you like, conservation law or condition, which is just that a thing that follows, remember, from the fact that PA plus m squared equals 0. We derived that in general when we discussed geodesic motion. And we derive that from the variational principle. And so in the massless case, of course, it just tells you that the tangent vector to the massless particles geodesic is null or light-like. And in the massive case, it gives us basically just the normalization of lambda, because it's telling us that in the massive case, it tells us, or in any case, it tells us that the element of proper time is equal to the mass times the element of this lambda parameter. Okay. So that'll allow us. So we have now three equations to work with. The one is conservation of energy, one is conservation of angular momentum, and the third is this condition. That'll allow us to eliminate, in some sense, 3 of the 4 variables involved and get a unique answer. More precisely, we'll use 2 of them to eliminate, I think, tau and lambda, and the other one will then give us what's left over, an equation relating r and phi. In other words, it's an equation for the spatial orbit. Okay, so we had the equations that we had were d lambda d lambda equals r squared d phi over j. Oh, I guess I should recall the definitions. So we called j, the conserved quantities were E, which was minus the inner product of the killing vector with the momentum, and E is so, the minus sign is so that it'll come out positively. It's a positive number when you choose the killing vector to point forward in time, which is a common convention. And then, of course, any killing vector minus that is still a killing vector, so nothing tells you which way it has to point. And then the other thing is J, which is the killing vector associated, which is the conserved quantity associated with the killing vector zeta 1, 2, A, and that's angular momentum, of course. So we have conservation. Those are the definitions of them, and that's when I write J and E, that's what it means here. Then from the other conservation law, we got dt is equal to E over J times R squared over H squared times d phi. Okay, so that's what you get when you plug in what J and E actually are in terms of dr, d lambda, d phi d lambda, and so on. You can see this allows us, this one immediately allows us, if we know r is a function of phi or phi is a function of r, then, and we'll generally treat phi as the independent variable, which is fine as long as you're not dealing with radial motion, because of course if you're dealing with radial motion, phi doesn't change, can't be used as an independent variable. But as long as it's not but if it's radial motion, that's very easy to solve separately. And anyway, it's not relevant to the two main things we're after physically, which is the precession of perihelion and the bending of light passing by the sun. So in both of those, phi is a good coordinate, at least for one orbit. It's a good coordinate. And then if you make it multivalued, it continues to be a good coordinate. And so if we know r is a function of phi, then we can get lambda, and we can get t also. You can find out the time delay, for example. So yeah, it might be nice to do the time delay, but I haven't done it. And so the only, so what's left that's not trivial when we substitute these things into the other condition, this condition here, that p squared is equal to minus m squared, we get, now where did it, oh, so we haven't done that yet, I guess. So we have to do that. So that's the thing we have to do now. So the third, I think that's where we stopped. So we have to now derive a relationship between r and phi based on that third condition, that mass shell condition, and substituting in what we know here. So the third condition then is that if I write it out in full, instead of just saying PA, treat them as both contravariants so that we can use this relation here. Well, where did I write it? I'm sure it's written somewhere, but I don't see it. So again, I'll write it. This familiar one. So using that, then we can substitute for P, and then we know the metric also. So what does that say? It says, if we do that, we get, what do we get? So this P, the metric is diagonal, so there'll only be 0, 0, or TT, if you like, RR, phi, phi, and theta, theta condition, contributions. But of course, it's not, it's in the equatorial plane, so the velocity in the theta direction is 0. So all we'll get is G00 dt d lambda squared plus GRR dr d lambda squared plus G phi phi d phi d lambda squared plus m squared which is, now we look back at the metric, G00 is minus h squared dt squared over d lambda squared plus 1 over, let's call it h to the minus 2 dr squared over d lambda squared plus g phi phi, which was, why have I written this? Oh, whatever. So g phi phi was r squared, d phi d lambda squared, plus m squared. Now I should further substitute what I know about these other things. So dt, if I divide these two equations, what do I get? dt by d lambda e, what is it, e over j h squared? No, e over h squared, is it? Is that right? See if you can check my algebra as I go along. Anyway, e over h squared, that's dt by d lambda, just from these two equations. Then we have h to the minus 2. Now we have dr d lambda. We don't know yet, but I want to get rid of lambda. So instead of writing d lambda, I'll write this, r squared over j d phi, d phi squared plus r squared, and then I'll d phi d lambda. Again, what do we have? Phi d lambda from this thing is equal to j over r squared, I guess. Plus m squared. And this is all equal to 0. Okay. So from here on in, it's just algebra, really. And if we rearrange this, so this becomes, taking this term first, what is it? Becomes j over r squared, j squared over, let's see, what do I have? J over r squared times 1 over a. Did I do this right? H squared. dr d phi squared minus, so what do we have here? E squared over h squared plus j squared over r squared plus m squared. This equals, as always, g equals 0. Okay. Well, now if you look at this, you see that you have just one equation for dr d phi. I mean, the only derivative is in this term, so it's dr d phi. So if I solve this for dr d phi squared, then I can integrate it up and get easiest to get phi as a function of r, because everything, this says h, but the h depends on r, not of course on phi. So everything else depends only on r. So if I split off this term, I could get an expression for phi would be some sort of integral, for r, no, what am I saying? For phi, would be some sort of integral of dr over some sort of expression involving r, purely r. I could do that, but it's actually, so you see that the problem is essentially solved, or as people say, reduced to quadrature. That is, means you just have to do one integral to get the answer. But it actually turns out to be more convenient not to do that and to substitute. So now it's just a question of algebra, as I said, but it turns out to be more convenient to introduce a new variable, which is 1 over r, or to make it dimensionless, let's call it r naught over r. So we called u, which is this 1 over r. And then in terms of that new variable, h squared is equal to 1 minus u. And it's also true, just by differentiating, just from the fact that u is basically 1 over r, of course, it also follows by taking logs, the du over u is equal to dr over r with the minus sign. So, okay, so now that we have all of that, let's see how someone has figured out somewhere along the line, I think probably in doing Newtonian orbits, that it's more convenient to work with the 1 over r than to work with the r. So let's re-express this equation now in terms of this. So if we multiply this whole thing through by h squared r squared, so let's take this equation. So we'll get j squared h squared over r squared 1 over r squared. I haven't done anything yet. Dr squared by d phi squared minus e over h squared plus j squared over r squared plus m squared equals 0. So now if we go and if we multiply through everything by r squared, what will happen? Did I leave something?
Sorry, the h seems to jump from the denominator to the numerator. Yeah.
Oh, that was a bad thing for it to do. Yes. Okay. So now if we multiply through by h squared, now that it's where it should be, this will go away. This will go away. But we'll get well, it should be here that we'll get an h squared. And here we'll get an h squared. And then if we furthermore multiply through by r squared, then this will go away. We'll pick up an r squared here. This will go away. Sorry? E squared. Oh, e squared. Good point. Any more mistakes? Let's see. So now, at least this term looks reasonable. So we'll get j squared. So what is this? dr over r is minus du over u. That's the point. So this will be j squared again. There'll be a 1 over d phi squared. And it'll be du squared. And then it'll be over u squared. That's the main thing. Then this, where's the j squared term? Let's look at this. This h squared is 1 minus u, I believe, yes. 1 minus u, j, something didn't work here. This should have been over r to the 4th, shouldn't it? I had to square, is there something that got lost here? Yeah, this was squaring this. J squared over r to, no, this is right, j squared over r squared. I claim that the right answer here, this goes to the next term. Yeah, that's fine, okay. So it's h squared times, so 1 minus u times j squared, and then plus the e squared term, which is e squared r squared, e squared r, I trade r squared for r naught squared for r naught over u squared, which is r naught squared over u squared. And then I have another thing multiplying m. Again, r squared, h squared. So again, it's r naught squared. Oh, what am I doing? R naught squared over u squared. Right. And then h squared, which is 1 minus u again. And m squared equals 0. Then I want to further multiply through by u squared over j squared. So this will go away. This will go away. We'll get u squared here. This will go away. We'll get 1 over j squared here. This will go away. Well, it'll turn into j squared, I guess. Okay, does that look good? So the upshot then is that du d phi squared plus there's a factor of 1 minus u here that I can pull out from those two terms. 1 minus u times whoops. Is there a sign mistake here? U squared.
Yes. The minus is in front of the e squared.
Here. Was that supposed to be minus? Yeah.
It looks.
How did I get this minus sign? H. Oh yeah, minus. That's right.
The minus sign is right, but in the last equation, you wrote it in front of the 1 minus u, but it's not in.
Oh, I should have written it here. And here it should be plus. Good. Okay. So 1 minus u times u squared plus r squared plus r naught m over j squared. And then now we have the minus sign where it belongs. We can put this on the right-hand side, and it'll be e r naught. Good. Okay. E r naught over j squared. Now, so that's the basic. So that is the basic. I mean, that's just this equation we had before, but now in nicer variables. So all we have to do now is analyze the solutions of this equation in some suitable approximation. So let me give this a name. I'll call this r naught m over j. This is just a constant, right? Some sort of positive constant. I'll call it a, and this other thing, e r naught over j, I'll call b. So now the equation takes the form, and I'll call this whole thing p of u. So it's just, you see, what the substitution of 1 over r made everything polynomial. That's all it did. It just made it convenient in that way. So the equation is now du d phi squared plus p of u, some polynomial, equals p squared, I guess I have to call it. Where p of u is equal to 1 minus u times u squared plus a squared. So if we plot this, so of course, so now u is 1 over r. So when you go out to large u, you're going to small radius, and when you go out to u equals 0, you're going to infinity. And then if I plot p of u, then I get, it looks, well, it can look in different ways, but the depending on the values of A and B. But let's look, here's a typical case. This will be the case that'll be of interest for the planetary orbit. So why have I drawn it like this? So you see that it's a cubic polynomial. Here it is. So, and for negative u, for large negative u, it's minus u cubed. So that's a very large positive number. For large positive u, it's a large negative number. And then the question is what it does in between. So that is, where are the roots of, where are the extrema of p of u? And it obviously it goes through 0 when u equals 1. So this is u equals 1. Remember, that means that r equals r naught. So this represents the Schwarzschild radius. If there were a black, which would be inside the sun, but if it were a black hole, this would be, that would represent the horizon of the black hole. So this is the Schwarzschild radius. Which for the sun is just a few kilometers, and so it's well inside the sun. So it means that this whole discussion doesn't work, breaks down before you get to that value of u, because you'd be inside the sun. So where are let's find the roots of this thing. Where are the minima and maxima, which are the roots, so the extrema of this curve, this polynomial p, are, of course, the roots of p prime of u is equal to 0, which, if you work out what it is, it's 1 minus, maybe I'll just write it out, so since it's just trivial algebra, which I'm more likely to make a mistake than get it right anyway, so it's equal to minus, so this just means that it's minus 3u squared, if you do the algebra, plus 2u minus a squared. We want to set that equal to 0. Of course, notice b drops out. This is just a quadratic equation for u, and you find that p prime of u equals 0 if and only if u is equal to 1 plus or minus the square root of 1 minus 3a squared over 3. Okay. So the important thing is that it has roots. So it means that the value of a here, which is really what a really is, at least if you turn it upside down, then you have j over m. So that's just the angular momentum per unit mass in units of the Schwarzschild radius. So it's whether the angular momentum per unit mass is big or small compared to 1 over the Schwarzschild radius. So for relatively more or less angular momentum per unit mass, you'll either have purely imaginary roots, meaning that there's no extrema, that it'll just be monotonic, or purely two real roots, which is the situation that I showed here, or the sort of marginal case in between. So the three cases that we just talked about are determined by whether a squared is equal, greater than, or less than 1/3, right? So now it's convenient. Now the analysis can be done a little more conveniently if we split it into the case of massless and massive. So far, we didn't make any assumption about whether the mass was 0 or not 0. Let's assume now, for the moment, that the mass is greater than 0, so that a is not 0. If a were 0, then one of the roots would go over to 0. It's a little bit different than this picture shows. So if we assume that m is greater than 0, then the picture can look like this, but it need not. So as I said, there's three cases. So the first case, where a squared is greater than 1/3, so there will be this discriminant or whatever it's called is imaginary, negative, so there are no real roots. So here we go again. So that corresponds, A being greater than 0 corresponds to J, the angular momentum per unit mass, being less than the square root of 3 times R naught. Oops. Yeah. Square root of 3 times R naught. And in that case, there are no roots, except for this one at the Schwarzschild radius itself. And so the picture looks like, as always, it goes through a squared at u equals 0, of course. And it's just doing something, it goes through 1 here, and it's just doing something like this. So what does that mean? We're thinking of phi, we're thinking of u, as a kind of space coordinate, and then if we think of phi as a kind of time coordinate, this looks like the kinetic energy if phi were to be thought of as time, which it is kind of a time, I suppose. I suppose that is how we measure time when you come to, at least how we used to, just by phi of the Earth, right? So if you think of phi as a kind of time coordinate, then this is kinetic energy plus potential energy equals total energy. B squared plays the role of total energy, and P of u plays the role of potential energy. So this is a graph of the potential energy now, and then the total energy can be chosen wherever, but not to put us inside the black hole. So total energy could be anywhere here, but wherever you choose it, you see that there's no turning point. So either you start at infinity and fall into the black hole, or there will be a time reverse, into the sun, it would be in this case, or there'll be a time reverse solution in which you emerge out of the sun at high speed and go off to infinity. Of course, while you're doing that, phi is time, so it really means it's an orbit something like this, perhaps, but it ends up ultimately falling into the sun. So that's that case. That's not the case that's relevant to perihelion precession, since it doesn't have a perihelion. So it's not the case of the planet. The second case is the opposite, that J over m is greater than the square root of 3 times R naught. So, the reason you fell into the sun here is that J was small. You didn't have enough angular momentum. You're almost falling radially, and it wasn't enough. So that's unlike, of course, Newtonian gravity. You'll always have enough. There'll always be some. So here you're seeing already an important difference from Newtonian gravity. Newtonian gravity, as long as you're not going strictly radially, you'll always come back out and make a closed orbit. Or if you're going fast enough, you'll come back out to infinity. But here you'll never come back out to infinity unless you have enough angular momentum. Oops. So in the second case, that's the one like what I drew over there. So that second case is like this, and then this. So how does it look? And then the third case, which is, I suppose, only of theoretical interest, is that they're exactly equal. So this is the critical case of the marginally stable, marginally stable. So we'll have, what is it called, a point of inflection here, where the slope is 0. And this will, if you work it out, or maybe it's obvious, this comes at u equals 1/3. Why is that? Oh yes, here it is. Because that's the case where the square root is 0, so u is equal to 1/3 plus or minus 0. So it's a double root here, So that, and this, if it just sits here, so this is a situation where if you start anywhere else, it'll just look like before, but there's one possible special value of the energy, which if you choose just that energy, you can just sit still at that point. So that's what you call marginally stable or marginally unstable, in the sense that if you make a linear perturbation, nothing happens to first order, but then to higher order, it'll either fall in or go out, or what am I saying? It'll fall in ultimately. So, yeah, it'll fall in. So that says that since if you sit here, the velocity is 0, that means the radius is not changing, but phi is changing, and that means you're just. So what is this? What is an orbit where the phi changes and the radius doesn't change? That's just a circular orbit. So this is some sort of marginally unstable circular orbit. For whatever it's worth. So it's just going around like this, but if you perturb it slightly, it'll end up spiraling into the sun again. And then the main case of interest, the one that corresponds best to the things in the solar system, is then this one. So one thing to notice, in this one, so let's go back to this one now. So here we have two extrema, and so that means there are two. So each of these is a place where this imaginary particle can sit at rest, right? If it sits at rest here, this is stable. If you perturb it slightly, it'll just oscillate around back and forth there. But this one, and in fact, that's what the planets really do, because none of them are actually following circular orbits. They're all following quasi-elliptical orbits. So they're actually bouncing back and forth here, but here at a larger u, which means a smaller r, there's another circular orbit, but this one is unstable. So these are both circular. Here's another circle. Two possible. This obviously is unstable. If you I don't think I said that right about the stability. What's the statement? That's probably okay. Yeah, probably okay. So this one obviously is unstable. So if you perturb it slightly, in this case, either if you push it slightly inward, then it'll spiral into the sun. If you start it slightly outside, it'll actually be a very. I'm not sure what it'll do actually. It depends on the relative heights here. It might just go up to infinity, I think, actually, but I'm not actually sure what it does in this case. No, it can't go. It might. Yeah, I don't know. Does anyone know? This one here. If he kicks this way, yeah. In any case, it'll go out to a quite large radius. It'll.
Come back.
Well, that's what I'm not sure. So I think somehow that this is higher than this. If that's true, then it means it'll make it all the way out to infinity. On the other hand, if this, you have to plug in and find how high is this peak here. This maximum, is it greater or less than a squared? Can be worked out, but I don't remember. I believe it's greater than a squared, but I'm not certain of that. So anyway, it'll either go So what it's doing is here's the star, here's the sun. So this thing wouldn't actually be relevant in the solar system because it would be inside the sun. But if there were no, if the sun were very compressed or were turned into a black hole or a neutron star or something, there could be an orbit like this. And it would be, out here you'd have the regular kind of quasi-Keplerian orbits, and then in here you'd have this very high speed orbit, and which is unstable, and I guess And if it gets slightly kicked out, then it'll just, it's got enough kinetic energy that it'll just keep spiraling out and maybe go forever to infinity. I'm not sure. But in any case, it's unstable and it's inside the sun. So it's not directly relevant to the solar system, but it's very relevant to, say accretion disk or things that are in the neighborhood of a black hole. Okay, but for these classic tests of relativity, we just need to look at this kind of orbit. It's a curiosity, or it's an interesting fact, that for every stable orbit, there's an corresponding unstable orbit, which is nearer in to the source. And those two, but when I say that they're corresponding, I mean that they both have the same value of the angular momentum. Okay. So we can think of all these different cases. There also should be a case there's also a case where it starts at infinity, falls in. Oh, that's right. So I think that proves that this has to be higher, doesn't it? Because we know when you get far away, we know that there are we know there are solutions like comets, which start off essentially at infinity, come in, circle around the sun, and then go back out to a very, very large radius. And in the limit, we know we could drop something from infinity, so to speak, or send it in from infinity, and it would come in. It would never get anywhere close to the sun. So the Newtonian, or it might be going very slowly, but it'll follow one of these hyperbolic orbits, throw it in, or parabolic orbits. So that means there must be solutions which reach infinity with a finite speed. So we can even start from infinity at a finite speed, come in, and then bounce back out and go out to infinity, right? That's an orbit like, here's the sun again. That's an orbit, one of these hyperbolic orbits, right? So it's something like this, which arrives at infinity with a finite speed. So I guess that proves that this has to be higher than this, because it can start here with a finite speed and nevertheless reach a minimum radius and then turn around and go back out to infinity. Okay, so now let's focus in on this question of the, let's do the case of m equals 0 first. Then focus in on the perihelion shift and the bending of light.
Question?
Yeah.
Does this mean that nothing that comes from infinity can fall in?
Oh no, it can, because we had this, if you remember. No, it doesn't mean that. If it has enough angular momentum per unit mass. No, in fact, you could start, even here, you could put the energy high enough, that is, send it in, for that given amount of angular momentum, you could send in, at a high enough velocity, aiming it towards the sun, roughly, and then it would make it over this hump, right, and then it would fall all the way in. And of course, the purely radial orbits will always fall in, but we've excluded them in a sense by demanding that we should be able to treat phi as the independent variable. It should be that the angle should be a good variable along the orbit. But they, of course, will fall in too.
Does it really have to do with the energy you're giving it?
I think so.
Like you're aiming it?
Well, it has to do with both, right? So the way we've chosen to analyze things here, we took, because just looking at this equation, it's convenient to treat this as a potential energy and this as a total energy, fictitious sense. So it's also convenient, therefore, to organize the analysis by taking cases in which you fix the potential energy and think of the total energy varying. So fixing the pseudo-potential, fictitious potential energy really means fixing the angular momentum per unit mass. And once you've done that, then this total energy, that's really not the total energy, which would just be E. It's really the total energy per angular momentum, right? I mean, some strange combination of the energy and the angular momentum. But it gets very large when you have a lot more energy than angular momentum. So that's you're aimed fairly directly at the sun, right? Because you have a lot of speed, but you're not very much angular momentum. And then the other case would be sort of the opposite, like if you're moving radially, tangentially, circumferentially, then you would have both a lot of energy and a lot of angular momentum. Okay. So let's consider now the case of zero mass. Yeah, let's consider the case of zero mass. And that means that this thing that I've called A is 0. Now the polynomial becomes even simpler. P of u is equal to u squared times 1 minus u, which we can also graph. So it looks a lot like the other one, except the one that we've been just talking about. So this is P of u. This is u equals 1. The only difference is that now one of the roots is actually at u equals 0, as one can see here. In the neighborhood of u equals 0, it just looks like a parabola. And of course, u negative has no meaning physically, as far as I know, because that means beyond infinity or something like that. Or negative radius, I don't know what it is anyway. So this part doesn't really matter. And so now we see that in this case, so this is now we're talking about photons. So we see that there's a single circular orbit, and it's unstable. This is a famous fact about the Schwarzschild metric. Again, it would be, of course, inside the sun if we tried to apply it to the solar system. But actually, light can orbit around a black hole, for example, in a circular orbit, but in an unstable way. So again, you either perturb it a little one way, it'll fall into the black hole, or you perturb it, or maybe even some other compact object, and you perturb it the other way. Well, probably not, but anyway, perturb it the other way, it'll go out to infinity, which is what you would have expected to see. So it's of interest to ask where this is. Where is this root? So if we differentiate this, we get so p prime of u is 2u times 1 minus u squared, hopefully, which is 2u minus 3u squared. And that equals 0 if and only if u is equal to 2/3, is it? 2/3, yes. But u was equal to r naught over r, so it means r is equal to 3/2 r naught. So it means that this circular orbit unstable for photons is at 3/2 the Schwarzschild radius, which if you wrote 2m, which is really 2gm, I suppose, for the Schwarzschild radius, then this would look like 3m. So you would say r is 3m. So you'll often, this is not the convention I'm using, because this requires you to set g equals to 1, whereas we're setting 8 pi g to 1 when we do it. But anyway, you'll often see this described as the circular photon orbit at r equals 3m, which means 3/2 times the Schwarzschild radius. Notice that that's closer. I don't. Again, for what it's worth, it's closer than this other unstable circular orbit for the massive object, which is at u equals 1/3, so it's at r equals 3 r naught instead of 3/2 r naught. Okay. So so now we have the massive and massless case in general terms. Now all we want now is all this stuff. We want the perihelion shift and the light bending corresponding to this. Perihelion shift is this case, and light bending is this case here. Okay. So let's do the perihelion shift. So now, so what the situation, so you can actually get an exact answer for it, but not in closed form, but in the form of an integral. But since the interesting case is, in fact, we can get a closed form answer. Let's do that case. So that's the case. The solar system case will assume a weak field. So if you remember when we were talking about weak field, in other words, nearly Newtonian gravity, we know that means that this phi thing I called phi before, I think, which is the Newtonian potential, like the GM over R kind of thing, that thing is much less than 1. So it means GM over R. This big M is the mass of the sun, or whatever is producing the field, should be much less than or equal to 1, which means in geometrical terms, this thing was basically the Schwarzschild radius up to some factor. So it just means R naught is much less than R. So you're very far out away from the Schwarzschild radius, and since we're using 1 over R, that's the same, or R naught over R, that's the same as saying U is much less than or equal to 1. So we're sort of out. We have to be sufficiently far away from U equals 1. So under that approximation, we can simplify. I guess we don't need this anymore. We'll be able to get a simpler final answer. So let's recall the equation we had, du d phi squared plus, no, I'll restore what was p of u, 1 minus u times u squared plus a squared equals b squared, where a was, I don't know if it got lost, but a was the mr naught over j, and b was equal to e r naught over j. So now let's see let's expand this out, or rearrange this, sorry. So it says that du d phi squared plus, just rearranging these things, multiplying it out and rearranging. I want this equal to, so put this on the right-hand side. B squared minus a squared plus u a squared minus u squared plus u cubed. Okay, so I'll give this another name. I'll call this f of u. Now this thing, okay, so far still everything is exact, but if we want to think what this term means, this is of course b minus a times b plus a. Now let's think Newtonian. This was, each of these was r naught, it had a factor of r naught over j in it. And then otherwise the only difference between b and a is whether you have e or m. So it's e minus m times e plus m. Still exact. But now, if we think that we're dealing with things moving relatively slowly compared to light, then, of course, remember this E, this means the total energy from the relativistic point of view, in fact, from the curved space point of view. So the total energy includes both the rest mass of the object plus its kinetic energy. So this E minus m is just the kinetic energy. Sorry, it also includes, of course, the potential energy from the gravitational field. So this is the total energy, but neglecting the rest mass energy. So you might call it the Newtonian energy. And then this E plus m is basically just 2m, since we're dealing with slow velocities and weak fields. So this just becomes 2m. So to good approximation, this is just 2m times the Schwarzschild radius over the angular momentum squared times what you might call E Newtonian, which, using my definition of A, is also, because A was just this ratio itself, m r naught over j. So if I bring inside a factor of m squared, bring in a factor of m squared, I get 2 over m times a squared times E Newtonian. Okay. Do we actually need that formula? I'm not sure. Anyway, that gives a sense of what that constant term is. So now what I claim is that f of u is equal to, let's look at this f of u. It's again a polynomial, using this clever choice of u instead of r. So it's again a polynomial, and it's again a cubic polynomial. And therefore, and we know it has, because we're in this situation here, we know that it has 3, how many roots? Well, we're here, this I wrote without the total energy term. If I put in the total energy, we're interested in this kind of orbit. So the total energy, this b squared would be here, sitting here. And I subtracted it off. So this f is basically this, except with a minus sign, because I took it over to the right-hand side. So it's flipped over, but it has this character. So there are 3 roots, right? There are 3 places at which, with this total fictitious energy, the particle can be, will turn around, in which the radius will start increasing or decreasing. Anyway, so there's 3 roots for this thing. And so, therefore, there are 3 real roots. And therefore, it must have the form, if we call those roots A, B, and C, what did I do? If we call the roots A, B, and C, then we can write f of u is equal to u minus a times u minus b times, but it's convenient to, I mean, we want this to be a positive number when, because this is the velocity squared, pseudo velocity squared. We want it to be a positive number when u is between a and b. If I call the roots in order, a, b, and c, then we want it to be positive when it's between a and b. So it's convenient to put b minus u, and then we'll have u minus c. But if you like, but I claim that the sum of the three roots is 1 or something like that. So I can write this as 1 minus a. Should be c minus u, because we want this to be positive when u is small. So it's equal to u minus a times b minus u times. Now I claim that c is 1 minus a minus b. Okay, how do we prove that? That's because a plus the sum of the three roots must equal 1. And how do we see that? What's the sum of the three roots? Right? I mean, if we expand this out, we'll have a u cubed term, and then we'll have a u squared term, and the coefficient of that will be a plus b plus c, maybe with a minus sign. But when you look at the coefficient of the u squared, well, it shouldn't be a minus sign here. So we look at the coefficient here. Here it has a minus sign. So if we look at the coefficient of u squared, we see that it's minus 1. So therefore, the sum of the three roots is always the coefficient of the next leading term in the polynomial. If you set the first one to be just purely u cubed. Okay, I'm just saying something trivial in a complicated way. So you can convince yourselves that the sum of the three roots is 1, and therefore I can substitute like this. So this is the most general form of the polynomial. So what I've done is re-express the polynomial in terms of its roots, and that'll allow the integrals to be done more simply. Okay. Notice that also means, since we're assuming that u is much less than 1 in this whole story, then that means a and b are small numbers. The turning points are also at much less than 1. So a and b are small numbers, so that means the third root is near 1. So the third root is actually very close to u equals 1. That's why it doesn't apply to, that's why it would be inside the sun. So this is the main thing we need now. Now the rest is just, at least until we get to the bending of light by the sun, we'll have to repeat this for the massless case. It's just doing an integral. So the question is now, so when you're talking about perihelion shift, what are you talking about? You have sun here, right? And you have something that looks very like an elliptic orbit, but maybe it doesn't quite close. Perihelion, of course, means, I don't know what must mean close or something. It's the closest point to the sun. Yeah?
Sorry, do we have to check the normalization of that?
Yes. What do you mean? Is it wrong? Is that what you?
Do we have to check if there's a factor in front of it?
Yes.
Oh, wait, no, I suppose there wouldn't be, since u cubed is just at order, is just 1.
It's just, yeah. I mean, it's important to get the factor right, because that governs the relation between the radius and the angle. Okay, so what's happening is it goes from the sort of minimum point, this so-called perihelion, to a maximum distance from the sun, and then it goes around again back to a minimum. It's by symmetry, it's obvious that the angle that elapses between minimum and maximum is going to be the same as the amount that elapses between maximum and minimum. So we just need to compute the elapsed, or the amount of angle traversed between minimum and maximum, and then double it, and that'll tell us by the time you get back to the minimum, that is the next perihelion, how much has the angle changed. And if it's exactly 2 pi, then there's no perihelion shift. But if it's anything more than 2 pi, then there's a slight advance of the perihelion. So that's what. So now this minimum, that's the minimum radius, of course, and the maximum radius. So it's the other way around. It means the maximum mu and the minimum mu. So let's Gesundheit. So we have du squared is double Gesundheit, I guess. So we have du health and health on top of health. So we have du. Our equation was du d phi squared is equal to f of u. And so the angle that is traversed between the minimum and maximum, the minimum, this is the minimum u and the maximum u, which is maximum radius and minimum. Doesn't matter. We want to compute that and then double it, and that'll give us the amount of angle from one perihelion to the next perihelion. So this is the integral. See, when I write a and b here, those are by definition now the roots of this f. Oh, I should have probably drawn a picture of f, although it's just the picture we had before turned upside down, but it's probably a good idea to draw it again. So here's f of u. So it's just the picture turned upside down and shifted so that the roots, so that b squared equals constant line becomes the horizontal axis. So here's a minimum, here's b maximum u, here's 1, here's the other root, which we saw is very close to 1 in the situation of interest, and the thing looks like this. This is now giving the velocity. So what we're seeing is that the velocity, when this crosses the axis, then when there's a root in this f, that says the velocity is 0, that's a turning point. So it's going from minimum u, maximum radius, down to minimum radius, and then coming back out. And all the while phi is advancing. We just want to know how much phi has advanced by the time you do that twice, the complete bounce. So the where were we? Yeah. So the answer is. So what this means. So the I see what this is. Yeah. So that's just a simple integral, right? So we just need to invert this equation, d phi du. I mean, now we're thinking of u as the independent variable, and asking how much phi changes. So we just turn this upside down, and we get 1 over the square root of f of u, and that equals. So this, in a sense, is the final answer. Is du over, now we need this complicated thing, u minus a times b minus u times 1 minus a minus b minus u with a square root, where a and b are implicitly determined as the roots of that polynomial, which started life in this form, right? Whatever. So with a capital A and B. So you take the roots of this polynomial, knowing the angular momentum and the energy. You take the roots of this polynomial. That gives you little a and little b, and then you do this integral between a and b. And that's the answer. And so for the full orbit, that's the half orbit. So the full orbit is twice this integral, du over blah, 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 blah. And then the perihelion shift is this, if we subtract 2 pi from it, then whatever is left over is this sort of delta phi, the shift in the perihelion, right? So all we have to do, so that's that is the answer, if you like. So you could do this all in Maple or Mathematic or whatever. But it's a little bit useful to have to get a closed form answer that doesn't anymore involve an integral when A and B are small and U is small, which is the actual case of the solar system. So this is, yeah. So this is, oh, here, this is the half orbit here. And then this is for the full orbit down here. Okay. So the rest is just some playing around with algebra. So are there any questions at this point? Yeah.
For the historical case, the precession of Mercury, I've heard that there was a way to also get a precession term in the strictly Newtonian sense, but I can't remember what that was.
Well, I believe there is. So something like a quadrupole moment for the sun or something would also induce a precession. So if it's not strictly a 1 over r potential, then you'll get precession. Is that what you're referring to?
Yes, I just couldn't remember what method they used to generate a precession in that case.
Of course, there is a lot of precession. I mean, in the real case is there's a lot of precession having to do from the perturbations of the other planets, forgetting about the sun possibly having a quadrupole moment. I think this came up, well, so I believe the story is that the precession due to the other planets is much bigger than this relativistic effect. So they had to do a lot of hard work, even to know that there was a discrepancy. I mean, it's impressive. They had no computers, so it's impressive how they computed all these effects from I don't know which planets really are involved, but let's say Venus, Earth, Jupiter, I don't know which are the main ones, but they had to take them all into account. And then they found this tiny discrepancy, which they couldn't explain. And so that's sort of an interesting lesson in something or other, that you can't extrapolate naively from history, because history has different lessons, right? So it had happened once before with Neptune. They found that its orbit didn't match the Newtonian prediction, and they said, aha, so there has to be something else that we trust the theory, so there must be some other planet we don't see. And they somehow managed to find where the planet should be in order to produce the perturbation in the orbit that was observed. And someone said, okay, go look there. And they pointed their telescope there, and they found a new planet. That was Neptune. Neptune was a new planet, so the anomaly must have been in the orbit of Jupiter or something. I don't know exactly what it probably. Anyway, they found, so that was, the answer was the theory was fine, but there was some matter there that they didn't know about, some object there that they didn't know about. Then they tried the same trick with Mercury, and they looked there and there was nothing. And so the answer there was the theory was wrong. You had to change the dynamics. So in one case, the dynamical theory was right, but there were some objects you didn't know about. In the other case, there weren't objects you didn't know about, and the dynamical theory was wrong. We're in exactly that situation now with the cosmological constant. And so people are trying both avenues. Some people think, okay, the theory is wrong, that's why the cosmological constant doesn't behave the way we expect. And other people think, well, okay, there's something we don't, maybe there's some other fields we don't know about, or there's something about the parameters of the fields that will tune it to zero or something like that. Actually, and no one knows which is right at this stage. Actually, I think dark matter is a better illustration, than the cosmological constant, because it's not so easy to say which matter would change the cosmological constant to be the way you want. But dark matter is a very clear analogy. In that case, opinion is coalescing around one of the alternatives. But if you go back a few years, then you look, it's exactly the same story, except it's now orbits not of planets around stars, but orbits of stars around the center of the galaxy. And people looked at these orbits of the stars and they see that they don't follow the Newtonian, which is a good approximation to general relativity in that case. They don't follow the Newtonian gravity at all. The distant stars in the galaxy are orbiting much faster than they should be if all the matter that was visible in the galaxy was all the matter that there is. So now again you have two alternatives. Well, there might be some matter that we don't know about, just like there was Neptune, and that is called dark matter. Or there might be that the theory is wrong in some way, that at very great distances or very small accelerations, that the dynamics change, and that's called MOND, M-O-N-D, modified Newtonian dynamics, and that's been also proposed. And they've got a lot of success fitting galactic rotation curves with that theory. Now the evidence for the dark matter has turned out to be so strong that I think there's not much doubt left that it's there from gravitational lensing and stuff like that. But you can still find some people who are pursuing the other line. So it's an interesting story. I mean, you always seem to have, when there's an anomaly or a discrepancy, you always have at least these two choices. There's something there I didn't know about, or the things that I do know about are always there, but they don't behave quite in the way that I used to think they behave. Yeah?
Can delta phi be negative?
Sure, it could. It absolutely could. And then in that you would have, what would we call it? I don't know what the opposite of an advance, a retreat, I suppose, of the perihelion instead of an advance of the perihelion.
What would cause
But
that? Or why can you have both?
Well, I'm just saying that because I don't have any deep understanding why the sign comes out the way it does. I mean, in gravity, it doesn't come. It comes out in one particular way, but I don't see anything a priori. So we have to do this integral and say, is it greater than 2 pi or less than 2 pi?
Because if it can be made big enough, then you can have triangular orbits.
Oh, I see. Not strictly. I see. Approximately triangular. Yeah, I don't know. That I don't know. So, well, we have to do, I guess, maybe we should. I'm not going to finish the bending of light today, I see, so I might as well break at this point. So the rest is just to do an approximation to this integral. We'll see. I'll just tell you what the answer is. Not to keep everyone in suspense, in case you haven't read it already. To the approximation we're working in, the answer is delta phi, which is this thing, the difference from 2 pi is approximately equal to 3 pi over 2 r naught times 1 over r plus 1 over r minus. Where r plus and r minus means, the perihelion and the, what's the other one called?
Perihelion and
Aphelion or something. Yeah, the farthest. So that's the answer. But so all we'll do next time is just play around with this integral a little bit to show that if you expand out this 1 minus the small stuff as 1 plus that in the numerator, then you can do all the integrals explicitly, and you'll get that answer. And then we'll do the light, the analogous thing for light, and then we'll start on the next topic, which is the derivation of the Einstein equations, which means we have to do a little more differential geometry. We'll have to define the Riemann tensor and things like that.